Hello my friends, welcome to my channel. Today I'm going to look at and discuss alternating voltages and currents. To understand what alternating current and alternating voltages are, we have to start by looking at how electricity is produced. That is by going to generation, or how electromotive force is produced.
Every single day, I'm gonna make something great. That's my way.
Electricity is produced by generators at power stations, and then it is distributed through a national grid system or transmission lines to various industries and domestic purposes. That's where you have now step-up transformers that transform the power generated by generators through the transmission lines, and then later on step down for various uses: industry, higher voltages, domestic use, usually single phase. So to understand what happens, we follow the principle of electromagnetic induction by understanding the principle of electromagnetic induction. The alternating current generator is a good example that we can look at to find out how the EMF or electromotive force is generated in a coil. Now, here we follow the principle of Faraday's law, which says that a current is induced in a conductor which is exposed to a changing magnetic field. So you can play by either changing the magnetic field, or you can be changing the direction or position of the coil that will then get induced with electromagnetic force or with a current. So there are four ways that you can do this: by changing, by moving the magnet, or by moving the coil, or by rotating the coil in a magnetic field. In this example, you look at us getting one coil and inserting it in between two magnetic poles. Now you realize that from the poles, the magnetic field is going to flow from the north to the south, like so. The magnetic field or the magnetic flux is going to be concentrated on this area, so there's going to be a higher magnetic flux density, which ensures that the coil can produce enough induction current. So in this position that we see, the coil is perpendicular. It's not having any effect on the magnetic field. It's not cutting any magnetic fields, as the wires are positioned in this direction, the same direction as the magnetic field. And therefore, we have zero induction or induced level of voltage here. And then as we turn the coil to this angle slightly, we get a slight induction of voltage or current. And then when we reach the maximum value, which is the maximum position where the wire now cuts, or the coil cuts through these fields, then you have got the maximum induction or induced value of voltage or current. And this goes on as the coil moves until it reaches again a position where it has no effect, it's not cutting, and then it goes on to the negative cycle, and we produce an induced electromotive force, which is, as you can see, a sine wave, meaning it has got the positive values and the negative values. And so if you notice these positions, you've got no generation or induction, because there's no cutting of the electromagnetic fields by the coil. And then we've got the maximum points when you have the maximum cutting of the field. The waveform that has been shown is called a sine wave. It's the shape that is produced by an alternator, and therefore what we get from our main supply or our electricity supply is also a sinusoidal waveform. And one complete series of values is what we call a cycle. And then the time taken for an alternating quantity to complete one cycle is called the period, or the periodical time. And then the number of cycles completed in 1 second is called the frequency, f, which we can obtain from f equal to 1 over periodic time t, or t is equal to 1 over the periodic time. When we come to looking at the sine wave, like we said, the periodic time is the time taken for one cycle, which is this cycle from there to P. So this is the periodic time. And then the values that we have, the maximum value, EM is simply the maximum value. So this is the maximum induced voltage. And then from maximum on the negative side to maximum on the positive side, we call that the peak-to-peak value. Basically, then this value, E1, can be called an instantaneous value. So it's a value that is at any time of the cycle. As the cycle is going around, at any time we can calculate what we call an instantaneous value. There are other types of waveforms that you find. There's the unidirectional waveforms, which is these two here. And unidirectional waveforms are not called sine waves. They are varying with time, but they are not crossing the zero axis to get into the negative cycle. So this stays on the positive side, and we call these unidirectional waveforms. And then we've got alternating waveforms. They are not sinusoidal, but they are alternating. This is a square wave. We've got a sawtooth, and then you've got a triangular waveform, and then you've got this other type of waveform. Now, we call these alternating waveforms because they are cycling from the positive to the negative side of the axis. So we can determine the periodic time from the equations. This is just an example. Like I said, you determine the periodic time for frequencies of 50 Hz. So if the frequency is 50 Hz, the periodic time t is equal to 1 over 50, which gives us 0.02 seconds or 20 milliseconds. In another example, you have an alternating current that completes 5 cycles in 8 milliseconds, and you've been asked to find the frequency. You have to first find the time taken for one cycle. So in this case, we found the time taken for one cycle to be 1.6 milliseconds. And then that is the periodic time. So if you remember, one cycle, the time it takes to reach there, that is the periodic time t. And if we know the value of t, then we can use our equation f is equal to 1 over t to find the frequency. And in this case, the frequency has been found to be 625 Hz. Understanding of other values, for instance, instantaneous value, which I've explained, the peak or maximum value, which are represented by the letter m. Wherever you see the small letter m, it's indicative of a maximum value. Then you've got the peak-to-peak value, which is twice the value of the maximum value, as you shall see later on. And then you have the average or mean value. The average value simply is measured over half a cycle, and you have a representation of AV. The average value for other waveforms that are not sinusoidal can be found by first finding the area under a curve, and then the length of base divided by the length of base. And we use various methods, some of which are the trapezoidal rule, the mid-ordinate rule, or the Simpson's rule, to estimate or approximate the value of that area. Once we find the value of that area, we divide by the length of the base, and we find the average value. But for sinusoidal waveforms, sorry, this must be sinusoidal, a sine wave, what we obtain for a sine wave is the average value, or the mean value, is 2 over pi multiplied by the maximum value. And in this case, 2 over pi is the same as 0.637 multiplied by the maximum value. Other values that we look at are the root mean square, or the RMS value, which we call the effective value of an alternating current. That is almost the same as the heating effect of an equivalent direct current, which can produce the same heating effects as an equivalent direct current. This is represented by simply the capital letters I, V, and E, and etc. So whenever an alternating quantity is given, it is then considered already as an RMS value. For instance, in Zambia, we use 50 Hz. Our single phase circuits are between 230 and 240 volts. So we can consider that as 240 volts RMS value. The RMS value for non-sinusoidal waveforms is found by finding the area of that half cycle, and then you divide by the number of intervals. So in this case, we use an approximation method where we divide this by n intervals, and then we find the root mean square of that value by adding up these intervals, divide by the number of intervals, and we get that root mean square. For sinusoidal waveforms, we can find the root mean square value by having 1/√2 multiplied by the maximum value, or you can take these as 0.707 multiplied by the maximum value. You get the RMS value of a sinusoidal waveform. Other values that we look at are values like the form and peak factors that simply give an indication of what kind of waveform you're dealing with. So the closer you go to 1.11, then you are getting closer to a sine wave, and the further you move from 1.11, then the more the waveform is non-sinusoidal. So for a sine wave, what you are going to get for the form factor is 1.11, and then the peak factor for a sine wave is 1.41, and then you can find the form factor from RMS value over average value, or you can find the peak factor from the maximum value over the RMS value. When we come to the importance of understanding the equation of a sinusoidal waveform, we begin by first analyzing the sine wave itself. So we have a vector OA, and this vector is free to rotate, and we're saying that this vector is rotating anti-clockwise, which is in this direction, and as it rotates, it reaches a position B, for instance. And if we get a perpendicular line from B to the horizontal line here, what we get is BC line. And if we plot these BC lines, if we can have many lines plotted here as the vector or the phasor is rotating in this direction, then we can plot this sine wave. And this is what you see here. So what basically is being shown here is the plot of the vector or the phasor OA rotating at an angular velocity of omega, and when we plot that, we've got this sine wave from 0 to pi, which is 180 degrees, and then we go to 270 degrees, and then we come to 360 degrees, which is basically a cycle. When we get that perpendicular line BC, which now gives us an indication of the equation. So if we find the sine of omega t, which is this angle of rotation from A to B, then our sine at omega t is going to be BC over OB, and this gives us the sine wave. So the sine, and therefore BC, which is now the equation of a sine wave or a sinusoidal waveform, is equal to OB multiplied by sine omega t. So a sine wave may not always start from 0, and for this reason, the periodic function or the equation of a sine wave, this is what we call equation of the sine wave, is therefore given by y is equal to sine omega t plus or minus phi. Phi is for the phase angle difference as compared to the equation for the sine wave that starts from 0 position. So from 0 position, you've got this sine wave that is starting from 0. So this we call the reference phasor. We reference all the other waveforms to the one that starts from 0 as the reference phasor. In this case, the reference phasor is drawn horizontal line. This is the reference phasor. Any vector, any phasor that deviates from this reference phasor, we can understand it as either leading or lagging. So in this case, what you see here is we've got y2 that is starting with a plus phi, meaning this phasor starts earlier than the reference phasor. As you are coming from here, you first meet this phasor as the leading phasor, which starts before the reference phasor starts. So we call this phasor a leading phasor. We can say that if we have the positive angle, which is a plus angle here, it means that we have got a leading phasor as compared to the reference phasor. And in this phasor diagram, you're able to see that you've got the leading phasor with an angle phi that is leading above this horizontal line. If it's going to be below from here, from this angle, then we can consider it as a lagging phasor, meaning it's behind the reference phasor. So this is how you get and understand leading and lagging phases. And in this case, we've got a phasor or a vector y4, which is lagging the reference phasor. So if you look at this, when you're coming from this direction, first you find the reference phasor, which is at 0. So there's no angle addition to the reference phasor. The reference phasor is just simply sine omega t. No addition of angle because it's starting from 0. And then phi degrees later on, the vector y4 starting, and so it is lagging the reference phasor. It starts after the reference phasor has already started. And in this case, you'll notice on the phasor diagram that this is lagging. It's below this reference phasor. And this is how you understand that these are important terms, that this phasor diagram is lagging. So you notice that for a lag, the angle is a minus for a phasor that is lagging. And for a phasor that is leading, the angle is a plus. So when you look at the general formula, what we see is that the value that is given here is the maximum value, and then you've got omega t plus or minus phi, which is the phase angle. To decipher this equation or break it down into smaller parts, we have to understand that the value of this sinusoidal voltage V is equal to Vm is what we call the maximum or the amplitude or the peak value. And the next value, if we multiply, if we double the peak value, then we're getting what we call the peak-to-peak value. If you remember, the peak-to-peak value is coming from peak to peak. Peak on the positive side and peak on the negative side. Omega here is the angular velocity. Angular velocity is 2 pi f, and then we also know that, so this is what I'm talking about, the angular velocity is 2 pi f, and from there you can also find the periodic time, because you know that frequency is 1 over the periodic time t. So when you replace that by 1 over t, then you can find the periodic time to be 2 pi over omega, which is in seconds. And again, using that same formula, you can find the frequency f to be equal to omega over 2 pi, and this is given in hertz. Phi, like I said, is the angle of lag or lead compared with the reference phasor. Now let's look at one example. So the example says an alternating voltage is given by V is equal to 282.8 sine 314 t volts. You are to find the RMS voltage, the frequency, and the instantaneous value of voltage when time is equal to 4 milliseconds. When we look at the solution, first you have to decipher what this equation is saying. You remember from the general equation, we are saying V is equal to Vm sine omega t plus or minus phi. So what we have here is Vm is equal to 282.8 volts. So the maximum value here has been obtained as 282.8 volts. Therefore, we are asked to find the RMS value, which we know is 1 over root 2 or 0.707 times the maximum value. And this gives us 200 volts as the RMS value. And then the frequency we can obtain from the given omega. We know this is omega t. So in this equation, there is no angle. lead or lag angle. So what we have is omega is equal to 314, and we know that 2 pi f is equal to omega. So from that we can obtain the value of the frequency, which is 314 over 2 pi, to get the value to be 50 Hz. When time t is equal to 4 milliseconds, we are saying when this t is equal to 4 milliseconds, what's the value of voltage? And we are saying we replace that time t, 4 milliseconds, so it has to be given in seconds, which is 4 times 10 to the power negative 3. And when we multiply that, we get this value. The value that we get in here, this is in radians. You must be very careful with this. This value you get is in radians. To get the actual value, we have to convert this radian value to degrees. To convert to degrees, what we get is that we take the radians multiplied by 180 over pi to get to the degree value, which is 71.96 degrees. And this is what we replace in here to find the actual value of the instantaneous value of V when time t is equal to 4 milliseconds. So this is how we obtain the value to be 268.9 volts. That's the procedure in a nutshell. AC values are straightforward and simple. I hope you enjoyed and you like that explanation. Now, for more examples, I suggest you look for a book by John Bird, Electrical and Electronic Principles. It's in chapter 14, and it's got quite a number of examples that you can go through and understand and practice. Thank you for joining me. See you next time.